Okay, so let's continue our discussion on perturbative QCD. So to revise ourselves, just look at the full Feynman rules which we have covered in the last previous lecture. So we had Feynman rules for the main thing is so the main difference between the QED and the QCD Feynman rules is that you have a color factor and self interactions of the gluon fields. Okay, see, these are the two main things which make a difference for the uh, compared to say QD. Otherwise, the entire thing is the same. Essentially, you start with a color SU3 color gauge group, demand local gauge invariance, gauge invariance. Uh, this leads to what do you call as gluonic fields. Write down the Lagrangian, and this gives you the Feynman rules. The only difference between QED and QCD is that now you have a larger group which is SU3 color, because there are three colors and all the three colors have to be really conserved, and the colors interact with each other, and so SU3 has 8 generators, so the out of which 2 of them are diagonal. So all these details we have seen already. So just to revise without putting in all the factors correctly, just to revise ourselves, remember the main things are there is this quark gluon vertex, which again has GS, which is the strong coupling constant. So there is a color factor here, there is a color factor here, and there is a color factor in the gluonic vertex essentially. So all these things will set up in lambda A, which is the uh, what do you call the gluon, or it is the generators, which is the coefficient with which the gluon is interacting. So eighth gluon, so A is equal to 1 to 8, depending upon what the gluon is and what the color of the cork is. So suppose if the color of the cork is I and J, this is the color indices. So you will have something like this. So you will have a gluon which is each of the gluons would be interacting in this particular fashion. In certain cases, if the gluon so it depends upon which gluon and what is the strength, what is the interaction, what is the thing which in certain cases which we have seen, I could be one color and J could be another color. So there could be I could be an incoming color and J could be an outgoing color, anti-color. So something like IJ bar or something. You can sometimes you can note it, but it doesn't matter. But um, so the anti-color could be there. So okay. So sorry, I should put it in different color. So on so the gluon carries the main thing is the gluon carries color. So the main So the gluon carries color, and this, as you know, leads to various interesting aspects, which we'll see today actually. Now, one of the first things, let's try to do like QD like processes with QCD. First, most important thing is the value of QCD. Okay, value of the coupling constant. QD alpha, which is equal to essentially e square by 4 pi, e is very small. Okay, is around 1 by 137, and it can of course increase to 1 by 128 at q square, as we have seen, at mz square. Okay, meaning at the scales of hundreds of GeV. Now alpha s, which is a strong coupling constant, gs square by 4 pi, is 0.112. At low energies is already order 1. At lambda QCD at around few GeV, and it it falls down, so it is pretty large, so it falls down at q square, so 100 GeV. By an order of magnitude, it just becomes, say for example, at q square is equal to so it becomes 0.112 at the same energy scale, say hundreds of GeV. Okay, so at lambda QCD, alpha is around order 1. Okay, already, so it doesn't, so alpha should be less than 1. That is the definition of perturbation theory, that you need to expand things in terms of a small parameter. Okay, now but this perturbation theory is not really getting you still so you see that it's already at a non-perturbative regime, so you can not really apply perturbation theory at very low energy scales around lambda, around 1 GeV or something. Okay, in fact at the tau mass itself, at the q square is around 1 GeV itself, 1 to 2 GeV, it just falls down, meaning it is around 1. It increases to 1, and at q square is equal to hundreds of GeV, 100 GeV square. This is around 0.112. So first of all, it has an inverted behavior compared to QED, because QED increases with energy coupling constant, whereas QCD decreases with energy with coupling constant. Okay, the coupling constant decreases with energy. Now let's do a simple process, like say for quark gluon going into quark gluon. So how will you draw the process? So you can draw the Feynman diagrams exactly like in QD. Incoming quark, and then there's a gluon, there's a quark goes back, and the gluon comes out. Okay, again the same thing we can do. Okay, we know how to draw the Feynman diagram, so now you can know P1, P2, P3, P4. Okay, this is a T-channel process. Sorry, this S-channel process. There is no T-channel in this, so the other one would be a new channel in which quark, gluon, quark gluon, so P3, P4, P1, P2. Okay, you can draw all the so you can draw the Feynman diagrams where this Q, say for example here, let me call it just to so T, this momentum T would be sorry, this should be S. So this momentum S would be P1 plus P2 whole square. Now this diagram is not really okay. I had to change the second diagram a little bit. 1 second, I just change it. So this is sorry, there is an S channel and there is a U channel. So here there will be U is equal to P3 minus P1. Okay. So you have this particular two channels, which are the two diagrams. No, sorry, this is P4 minus P1 and so square. So these are the two diagrams you have for contributing for this one, for the process of core-gluon scattering. Now the point is that this again we have to if you do the amplitudes, let's start with the first diagram. If we want to do the first diagram amplitude, so here we have the gluon with the color factor A. So let's start with the gluon, epsilon mu. It's an outgoing particle with P4 star and the color factor A star. Okay, and then you have I GS gamma mu lambda A. Okay, and then we have the quark factor, which is outgoing U bar P3 with the color factor C dagger. And the propagator of the quark Q square, no, sorry, let me call it Q slash minus say MF. Now similarly for the incoming particles you can also add epsilon mu incoming P2 A I GS gamma mu lambda A. Then incoming U P1 C, the color factor. Now if you see this, this amplitude looks almost similar to the one that we have derived for the Compton effect essentially. So the first diagram, so this diagram, except so the way we wrote the amplitude, we wrote it almost the same way, except for a factor which is the color factors which are sitting here. These factors make all the difference. So these factors make all the difference uh, in the computation of the amplitude compared to QD. These factors form the color factor. So the color factor tells you what is the difference between a simple amplitude, say the same process in a QED compared to the color factor distinguishes the amplitude compared to the uh, similar amplitude in QD. So not only the you can evaluate the color factor. Actually, the color factor comes out into some combinations of say I think the C factors. Okay, so this will be some factors like this so C corresponding to the incoming quark, and then there will be a lambda, then there's another C. Okay, and then uh, so all okay, so this, and then is another lambda. So all these factors which appear here, and then there is a actually. So for each A, okay, so this combination is so called the color factor, which becomes much easier to evaluate uh, using the delta Kronecker delta functions. Actually, normally these are given in terms of Kronecker delta functions, because you notice that the incoming the color is always conserved, and the color is always conserved. So uh, so the main point is that we'll try to instead of going into the technical details, because we are not going to be experts on QCD. This is not going to be a QCD lecture, because we are just doing an overview of the topic. And the main point is that these color factors. No, so the QED compared to, so if you want to compare QED versus QCD amplitudes, okay. So versus QCD amplitudes. So first you have, okay. So here we have larger coupling constant. Here you have a smaller coupling constant. In the second also, then here no color factor. Here there is a color factor. at the amplitude level. So what you would expect is a larger enhancement of the amplitudes. Okay, a larger enhancement of the amplitudes compared to say QD. So compared to QD, you would expect much larger expansion, much larger amplitudes, and this would play a very interesting role. Say for example, let's just take say a simple QED process. Okay, so before going into more details about this one, so QCD itself, so let's just take a simple QED process like say something like E plus E minus going to mu plus mu minus. Now this is a process which we have looked into it. Okay. Now this has so taking time in this direction. So this has only one diagram. The photon so this is mu plus mu minus E plus E minus. Okay. Now just replicate this diagram. Now instead of taking mu plus mu minus in the final state, if I take say quarks in the final state, that is also quite possible because quarks also can be produced here. So let's, for definiteness, just take this to be one particular quark. Say let's say it's a B quark. B quark is heavy and so it doesn't it also forms bond states and hadronizes, but still let's just say that I form because I can identify whether the B quark has been produced or not at a collider. Okay, so with this idea what I do is I do the same E plus E minus but with a B quark. Now B quark the amplitude looks very similar. So, okay, except for the mass of the B quark, and if I take this energy of the exchange to be very high, so in that case I would expect that the masses of the final states don't really matter because all the masses can be just taken to be almost uh, so zero. Say for example, if the incoming electron and positron are moving around say hundreds of GeV squares, okay, with speeds about hundreds of GeV at energies about 100 GeV or 10 GeV, 15, 20, similar, something like that. So in that case, you wouldn't expect the masses like of the electron or the bottom quark or the muon really to play a role. We can actually take them to be almost like a massless case. Now compare uh, these two diagrams. Now if they are massless, they look exactly the same. They don't really make a huge difference except for the uh, this is a muon and this is a bottom. Now in the massless case, muon or bottom, it doesn't make a difference. Okay, but it makes it, one would expect that, okay, one would expect that the cross sections of the electron positron going into final states of mu plus mu minus and the cross sections of going electron positron going to two bottom quarks would be roughly the same. But this doesn't happen because the bottom quarks, these are uh, uh, these are uh, these are colored objects, so they come in three colors. Okay, so each bottom quark is actually produced three times. So what you call bottom is actually a sum of three diagrams in which there is one diagram like this, there is another diagram like this, where this is a red bottom, okay, this would be a green bottom, and okay, instead of that I'll just draw it in. Okay, it's a sum of three diagrams. So I had to sum or all the colors C is equal to I, uh, 1 I C, okay, C is equal to 1 to 3. Let me call it a C, some index C, which is the color factor. So you have essentially three diagrams instead of one diagram, and each diagram has roughly the same amplitude as E plus E minus as mu plus mu minus. So you are replicating E plus E minus so three times, because there are three colored quarks essentially. So what you expect if you take a ratio R sigma E plus E minus going into B bar, okay, to sigma E plus E minus going into mu plus mu minus, you would expect a ratio of the factor of 3. Okay, if this entire thing that the color is correct and everything, so you would expect a ratio of factor 3. And this is precisely what they found in experiments. Okay, they found a factor 3 difference between E plus E minus going to mu plus mu minus, and a factor 3 difference, okay, to say BB bar, and is roughly around the factor 3, which is roughly the concept of color. So bottom quarks have this color. Okay, so now this is the QED process. If we are just talking about QED, this is all QED process. It's not a strong interaction process, but purely because of the color factor. So we were looking at the distinctions between, let's say, QED, QCD, I mean colored objects and non-colored objects. So the colored objects always seem to be having more cross sections. Okay, they interact more, and they get produced more in, let's say, interactions with hadronic objects essentially. Okay, if you have a proton-proton collision, say for example like in LHC, you would expect to produce a lot more colored objects compared to, say, leptons or any of the other things, like which don't have any color quantum number. So, and the color quantum number would be is very high. I mean, color quantum number, the color factor is one of the important ingredients to increase the cross section compared to the purely just leptonic process, QED process only. Okay, so to come back to the point that you'd have not only just a smaller coupling compared to in colored particles. Okay, the second point, why QED is much weaker compared to strong interactions, is that there is this color factor which we have been talking about now actually. So, okay, then there is the other important factor. So then there is a self interaction. The third important point between QCD and QED is the self interactions. Oh, self interactions are absent of gluons are present. Okay, so this is so this is also the, okay, just to final point, experimental verification of color. This is actually how color was verified. One of the first, okay, one of the things through which you can verify color. Okay, now coming back to the third. So the third point, as I said, is that the self interactions are absent in QED, whereas they are present in the case of QCD. Okay, self interactions are present. Now this we will see in a specific case now. Actually, before going that, just let me just say that this ratio is actually one of the most important experimental verifications of color. Okay, Um, so going back, the self interactions also play a big role. The self interactions also play a big role and to distinguish between QED and QCD. The self interactions of the gluons. Of gluons. Now we have seen that there are two different vertices. One is a triple gluon vertex, and another is the 4 gluon vertex, which comes at GS square, and this comes at GS. Okay, and this is at the tree level essentially. Okay, at the leading order, this is the diagram for QCD, which appears, which is also called the triple gluon vertex. And this is the quartic gluon vertex. Now this has very important consequences in QCD. We'll see one or two of them right now essentially, which is important for us. So let's just take one important consequence. Let's just take say QQ bar going into two pair of gluons. Okay, okay, so let's just look at the diagrams which contribute to QQ bar going into pair of gluons. This is like pair annihilation of E plus E minus to producing two photons. Okay, this is very similar to that. Here in this case, you are producing two gluons. So the diagrams would be so the diagrams would be, you would say what similarly to happens in QD. So what the first diagram you would draw was the same thing which we had drawn here. Similarly, okay, earlier, sorry, yeah. Okay, and then there will be the cross diagram for this. So this would be something like a T-channel diagram, and then there is a U-channel diagram. But you would also expect, would there be there will be also a third diagram similar to, this is similar to QD except for the color factors. Okay, but then you would have one more diagram in QCD which is of this type. This is an S channel diagram, so in which you have quark and a quark, then a gluon, and then here you can see the triple gluon vertex playing a role. So because there is this vertex possible, due to the self interactions of the gluons, this diagram is also possible. So you have, in addition to these two diagrams which we have seen, which are very similar to the electron positron annihilation pair annihilation in QCD with or with for strongly coupled particles, okay, would have also have or for strongly interacting particles with the color, okay, would also have an additional diagram, okay, which is given by this system because of the because this is the S channel diagram. So this is because the gluons interact with themselves. So because the gluons interact with themselves, you'll end up having this kind of thing. So now you can ask the question. So you have gluons in the final state. So the other thing which we had to worry about is, okay, now we understand that there is except for the color factors, it's almost the same. Now gluons are in the final state. So how do they appear? So the gluons in the final state appear, should the two gluon state in the final should be in a color singlet state. In the final state should be a color singlet case. Okay, so similarly you can ask the question, so the initial gluon state also should be a color singlet state. Okay, initial quarks also should be in a color singlet state. So now talking about gluons, so one can ask the question, how do you discover these gluons? Meaning, how to discover these gluons in, let's say in an experiment, say for example. So how these gluons are discovered in an experiment, and how do they appear? Okay, and what is this idea of heterogenization? So, so this goes under the concepts of jets. Okay, so let's just do the same analysis which we have seen. Like for example, then there. Uh, so first there is. Let's just consider a process in which we have considered earlier. So this is E plus E minus. It's a photon. So photon goes to two quarks, say for example a quark of some color, quark anti-quark pair. The quark doesn't remain stable, essentially it doesn't remain as a quark because it has to confined, so it starts producing a gluon. This gluon then decays into a quark anti-quark pair, and the anti-quark will start forming a hadron or a baryon, meaning a meson or something, okay, with the initial quark, and this one again then deviates into another quark, okay, another gluon, and which again pairs off into this, and so this entire process in the end start reproduces, okay, a bunch of say pions, kaons, baryons and hadrons, mostly essentially mesons and baryons. So these all produces hadrons. Okay, this goes because this is in a typical collider environment. What happens is, if this is a collider, say for example this is a this is a collider, this is a point, and so these quarks interact at this particular point, the incoming electron positron interact at this point and produce these quarks. These quarks move towards the detectors essentially in this particular fashion, okay, in say if they are in opposite direction, and then all this bunch of particles are produced here. And these bunch of particles leave a shower both in say uh, hadronic calorimeter meter and also the EM calorimeter depending upon the charge. So all their energies is typically deposited in terms of bunch of particles. Suddenly you'll have a bunch of particles all at the same time being depositing the energy in the detector. So this is called a jet. This object is called a jet. So how do you calculate? You actually do some sort of an algorithm to calculate this jet. So there are several algorithms actually. Okay, these algorithms actually try to calculate what this jet is in a typical collider event, any collider event actually. Uh, and there are technical issues. Now, what do you expect if there is a gluon? Say, for example, if there are no gluons in nature, you would expect such an event, say E plus E minus going to QQ bar, just to have only two jets, say for example, or two jets, or not more than two jets, because a quark will heteronize and another quark will heteronize. We don't know what the gluon would be actually. The quarks will anyway heteronize because it could need not be heteronizing through gluons. Say it could heteronize by something else, so some other thing. But if there is a gluon, okay, if there is a gluon, you would have another event actually. You could have an event in which so E plus E minus going into QQ, and then one of the Qs could just radiate a gluon. Okay, one of the Qs could radiate a gluon, which itself could form a jet. So in addition to quarks having their own jets, if there are gluons, you should expect if the radiated gluon to have enough energy to produce a jet of its own. The gluon could have a jets of its own in the collider. Okay, so you could have, so instead of expecting just two back-to-back jets, okay, you should be in the gluon in the collider. You should expect some three jets, say for example, two of them in one direction, another in this direction. So in the collider, one would expect three jets, say for example, instead of two. This would happen for certain energy levels essentially. It will not happen for very low energies, but for certain and significant energy for the outgoing quarks, you would expect this kind of a thing. And this is exactly what they have found. I think I reviewed it in the discovery of the gluon in the initial first lectures. So the gluon itself could have its own jets essentially. Okay, so this is also led to the discovery of the gluons. So the self interactions of the of the self interactions of the particles, say for example gluons, the gluons could themselves radiate other gluons and everything, would also play a role because in creating this jet, not just the interactions with the quarks, the self interactions of the gluons themselves. Okay. Now there is also another very important aspect about the self interactions of the gluon, which play a role in something called the asymptotic freedom, which we have seen in. So we saw that there is an effective charge associated with uh, so if we have an electron here, so this is essentially like the question about what happens, how does the electric charge change. So we said there is an electric there is some electron sitting here, there is another test electron sitting there, and then said that this produces a bunch of a cloud of electron positron pairs all aligned here, and so on, so now we want to ask the same question, say for example with the quark. Okay, how does the quark strong coupling change with energy? Change. Yes, it does change, we know, but how does it change? So similarly, let's just take a quark here, and then it radiates a gluon, say for example, another test quark somewhere there. So this gluon while going to, so these are the tree levels, say for example, this gluon while going to the other test charge should be able to radiate, would be producing quark antiquark pairs of this type. Okay. Okay, then there could be other quark antiquark pair, there could be more, but okay, so these things will start interacting. Okay, but then you could also have gluons sharing things with each other, gluons sharing here, and so on. So but in addition, there could also be contributions coming from this kind of diagrams in which you will have gluons, gluons, and then you'll have gluons sitting here. Okay, and then there is a quartic gluon also, so you'll also have gluons sitting at the same bubble, so you'll have this kind of diagrams also. Okay, there could be large number of these things. Okay, so there are a huge number of diagrams. So these diagrams, self interactions, the computation is slightly complicated. I won't be able to revise the entire thing. Play a crucial role. In fact, it can be shown that these have an opposite sign. The triple gluon vertex contributes to the negative sign. Okay, to the evolution of the strong coupling constant. And so when you show that, when you finally calculate everything, it turns out when you finally calculate everything, it turns out that the coupling constant with energy, so this is alpha s, starts falling off with energy. Now this is completely different compared to the case where we saw about um, uh, about QD, where the coupling constant increases with energy. Here the coupling constant falls off with energy, and this is called asymptotic freedom, which we have discussed, that this should be one of the properties of any theory which describes QC. Now the fact is QCD shows this feature with 3 colors and 6 quarks which have been seen. So you don't need full 6 quarks, but anyway, so this actually you can compute this entire beta function or how the coupling constant changes with energy, and you can see that the QCD has this feature where the coupling constant falls off with energy. Okay, so more or less we have covered most of the features of QCD, and we can actually do other aspects of QCD. But I think I'll stop here. I think we have the one thing which we have not covered essentially is something called the we assume, okay, more or less we covered most of the aspects of perturbative QCD. So the one thing which we have not covered is something called the deep elastic scattering. So the quark model. Now deep elastic scattering actually predicted the existence of quarks, so verified the existence of quarks. Anyway, we got the quark model coming from the baryonic structure and the mesonic structures because we wanted to have all these things in terms of some flavor symmetry. You remember that we reconstructed all the quarks and baryons in terms of 3 quarks picture, and baryons what do you call classification already predicted the existence of quarks. But people were okay, they were, it was nice, the okay, it was sort of nice thing to look at, but people were not, there was no experimental verification. It's like some sort of a classification. For many people it was just considered to be some mathematical objects actually for a long time. Okay, so you'll see many people telling you that okay, these are just mathematical objects, and so there was not really any experimental verification of this thing, which was sort of uncalled for. But anyway, that was a history. But anyway, we can now the process which set this quark picture on a very strong footing is called the deep elastic scattering. Okay, so what is deep elastic scattering? Deep elastic scattering is essentially the scattering of electron on a proton. Okay, so the elastic okay, now for low energies, say for example, this is just electron proton scattering, say for example electron, you don't have a direct line. Okay, so you'll have simple diagrams like electron goes to electron, okay, and then proton goes to proton, and you exchange a photon like this. So it looks like a simple process in QED. Okay, this is like an elastic process, and what you expect to see is what is the internal structure of the proton, because remember proton is a composite object. So it won't see the exact the coupling. So the coupling actually is a bunch of things. It's a composite object, so it will be smeared by a function which is some form factors, some f of q squared, some form factor, okay, would be multiplying the electric charge combination here essentially. So the vertex here would be some I e say gamma mu some form factor f of q square. Okay, so instead of just I gamma mu like in QD, so in addition you will also have this form factor sitting here actually. Now, now suppose if you start increasing the energy, okay, at some point when the energy is very high, okay, the actually it starts seeing internal things about the proton. At some point, the photon starts seeing the internal workings of the proton. But if you really have very high energies, what happens is the proton gets disintegrated. That means you can break the proton with sufficiently highly energetic electrons. So they come, and so what is this process? The process is like this. So the electron comes and goes away, exchanges a photon, hits the proton, okay, and then the proton just disintegrates into some X essentially. So whatever is remaining here essentially there it remains something. Whatever is remaining of the part of the photon comes as this is the proton actually, and this just disintegrates. So what does it happen? So this is was a very interesting phenomena in which the electron not just seeing the internal structure of the proton, and the proton is no longer a proton after the interaction with the electron. So this is a very inelastic process. Okay, so the electron, the proton no longer remains a proton actually. So it just disintegrates, and so what? So people try to understand what this feature was. So people were computing the possible cross sections for this, assuming something called the structure functions. So what are the structure functions are essentially if there is some content of a quark or something inside the proton, so it contains some value. Okay, what is the probability distribution of this particular quark or substructure of the proton, which is inside that of a proton. But independent of that, essentially, that you had two forms. You can write down most general what do you call as the cross section in terms of two momentum species. So we have E photon. Let the photon carry a momentum q. Okay, and then this is all this debris x essentially, and then the proton could carry a momentum p. P is essentially the fraction of the energy which the proton actually takes. Essentially, the proton, this is the proton. So what one can do is so you can imagine that okay, there is a photon coming in with a large momentum q. So there is some sort of a process in which so the photon is hitting with the proton, and this is giving you some x. This is some new particle. So this is a bunch of new particles, each carrying several momenta. Say for example, plus some p. So typically what happens is if you hit an electron and a proton, it gives you a bunch of kaons, pions and all this business, plus whatever is residue essentially. So we call this as some, so something, some, it is the remaining part of the proton, whatever it is. So this could be say So if we just write it in terms of P1, P2, and then say P3, this is essentially the P, and then there will be P4 to Pn, essentially a lot of these things. So there is this process in which, remember, in which gamma, which is a spin 1 particle, proton, which is a spin half particle, giving you a bunch of particles like this. Inherently, this entire thing is sort of unknown. We don't know how is this happening. We just don't know what it is. You can represent it by some unknown function. Okay, so this unknown function, it turns out, after using spin averaging and everything, after and Lorentz, what do you call, Lorentz symmetry, and other tricks and trades, at the end of the day, it turns out to be it has only two parts, has only two parts, both which are dependent on two functions, essentially Lorentz invariant momentum variables. Q square and small x. So what is this q square? Q square is the energy at which the this and the same q square. This is small q square, and the small x is defined as 2 q square by p dot q. Let me just this x is also called the Bjorken x. Actually, it is called the Bjorken x. Now, this is essentially the fraction of the momenta taken over by the proton, actually. So, fraction of the momenta taken over, as will turn out, by some substructure of the proton, actually. Is the substructure. Why would you need substructure? I'll come in a second. Of proton will turn out to be, okay, it's essentially the fraction. No, but why do you need substructure? We need substructure because Bjorken predicted that these two functions, which are called f1 and f2, okay, which are called f1 and f2, they have, which are functions of q square and x, f1 and f2, which are also q square and x. He proposed something called a scaling, which says that at large q square, f1 of q square x is essentially a function of x, independent of q square. So this was a very important prediction by Bjorken, and soon enough Slack verified this the results of this thing. So for large q squares, say for example, they just become flat. So the data points are essentially flat. Further, you can also deduce the spin information. So what this tells you that, okay, one thing it tells you that the proton is definitely a composite object, and uh, yes, definitely is a composite object, which we already know. But it also tells you that at large q square it doesn't meaning it is sort of loosely bound, in the sense that the composite nature is more evident, that the constituent takes a central part. The constituent takes a central part, so it's no longer seeing the total momenta as it's not. So the total q square is not hitting the full thing like a hard ball. So okay, the proton is not like a hard ball, but a loosely bound composite of its constituents. So, so that is one thing. So it's already known that this is so it's not like it's lot of tells you that okay, there are proton is not really like a hard ball. So that means that it is made up of some loosely bound constituent. So and furthermore, so it's not like if these are quarks, say for example, like Gell-Mann has predicted, but there was some sort of bad blood between meaning Gell-Mann and Feynman and all the senior scientists at that time. So they started calling them as partons. Now we know that there is a difference between partons and quarks essentially, but at that time it looked like okay, this was just this is something which comes out in these are the particles which appear in deep inside a proton in deep elastic scattering. These are the constituents of the proton in the deep elastic scattering. Okay, these are parts, so these are called partons by Feynman, and so that name sticken actually. So each parton has its own structure function, and uh, anyway, so we'll see that no, the second thing was another important information came that there was a relation between this f1 and f2. So 2x f1 of x is equal to f2 of x, which was also verified by the experiments. So what this tells you is that the partons have spin half. So they are made up, this proton is made up of 3 spin half particles, okay, which are all having spin half. Essentially, if they have different spin, these functions actually vanish actually. So this led to the sort of uh, uh, verification or experimental verification or establishing led to the establishment of the quark picture. So now we had taken the quark picture very easily so far, but it required a lot of phenomenological analysis, okay, detailed data understanding, and understand the scaling feature, which was discovered by Bjorken, and uh, further the Gross Kalan-Gross relationship and establishment of the quark picture actually. Now Deep elastic scattering also tells you nowadays what we call high is as a part something called the parton distribution functions. Sometimes called PDFs. These are experimentally determined. They tell you the amount of or the probability distribution of a particular quark present inside a proton. So normally you have something called the valence quarks, which are essentially U and D. Okay, you know what the proton is made up of U and D quarks. But there could be other quarks also, like you said, because we have seen that QCD is made up of strongly coupling gluons, and these gluons can produce quark antiquark pairs. And if the energy, probe energy is sufficiently high, this quark antiquark pairs can produce other things like strange quark, even charms. Charms is less essentially, perhaps. So let me put a question mark here, and so on. So essentially, so strange quark has been there, but anyway, so there are charms which have a very low probability actually. This is not established actually, but anyway. But the most important discovery is the parton distribution function of a gluon, which becomes the dominant parton at high energies. Okay, at high energies, most of the proton is actually a gluon. Okay, most of the proton is actually a gluon. You don't really the rest of the particles don't really play a role actually, meaning it is most of the time it is essentially a gluon. Okay, at high energies. So at LHC, most of the time you are actually hitting two gluons with each other. Just a gluon. Okay. Okay. So like at LHC energies, proton is essentially a gluon. Okay. So this is essentially establishes. So now you can say, okay, quarks and partons are different because now you have parton distribution function of a gluon and the strange quark and so on. So now you can sort of distinguish between partons and gluons actually, partons and quarks. So this sort of ends my discussion on QCD, and the next 3-4 lectures I'll cover weak interactions, and we will stop that actually. So I covered most of the things which I have said about in QCD. Okay, we covered asymptotic freedom, we covered deep elastic scattering, we covered the quark model and perturbation QCD. These are the main things. We also covered a little bit about chiral perturbation theory, and also about just mentioned about lattice. So I'll stop my lectures on QCD here, and maybe we'll look into it. Okay, weak interactions later on. Actually. Okay, I'll stop.